In lecture 3, we're going to talk a little bit about the spontaneity or non-spontaneity of redox reactions and actually introduced some of the vocabulary associated with electrical flow or electricity in relation to redox reactions. Now, redox reactions, like every other type of reaction, of course, can be spontaneous, negative delta G, or non-spontaneous, a positive delta G. If you recall the spontaneous reduction of copper 2 plus ion to copper metal by zinc metal, this was shown in the previous lectures to be a reaction that's quite spontaneous where copper metal actually forms on the surface of zinc metal as copper ions reduced. The net ionic equation for this was solid zinc plus copper ion going to zinc ion plus copper metal. We can calculate a delta G under standard conditions for this redox reaction by using delta G of formation values and what should be a now familiar equation where we add up the delta G of formations of the products and subtract the sum of the delta G of formation of the reactants. The table on the right just is a table of the 4 values that we need here. This particular table is from a general chemistry book by Nivaldo Tro. You have available to you a table that has these values for many other ions and elements and compounds. But we'll just need these values right here. If we do this calculation, which is fairly straightforward, of course, we add up the delta G of formation values of the products, zinc ion and copper metal, realizing how many moles of each that we have, and we subtract the sum of the delta G of formation values of the reactants, zinc metal, copper 2 plus ion. We cancel out the appropriate units, and we end up with a standard delta G of minus 212.6 kilojoules. This is a very spontaneous reaction, as evidenced by the fact that the reaction goes by itself, which you saw in the pictures in the previous lectures, but also it has a very large and negative delta G value. Well, since redox reactions involve electron transfer, in other words, a flow of electrons, it's not surprising that the study of electrochemistry would require the use of terminology commonly found in the study of electricity, such as voltage and current. So we're going to spend the next few slides introducing some of this terminology. We will soon discover that redox reactions have calculated voltages that can be related to free energy values. So let's look at some electrical units and electrical terminology. I have a diagram here where we're trying to view a flow of electrons in a copper wire. The copper wire is this kind of orange colored line here. It's supposed to be copper colored. And electrons are flowing from left to right, from position A to position B. So you notice there's electrons coming in from the rest of the electrical circuit to A. The electrons are going to flow across this copper wire and then go to point B and then out to the rest of the circuit. So we have little symbols for electrons here flowing from left to right. Now, one quantity of interest would be the total charge flowing past a defined location in the wire. What this means is that we basically will be counting electrons flowing past a defined location in the wire. The unit of electrical charge is the coulomb. Now, early in general chemistry, students are told that an electron has a -1 charge. What this really means is 1 unit of negative charge, with 1 unit of charge being equal to 1.602176565 times 10 to the minus 19 coulombs. This number is known to high precision. We often see it written with fewer significant figures, maybe something like 1.602 times 10 to the minus 19 coulombs. Now, 1 mole of electrons, meaning if we count 1 mole of electrons, that 1 mole of electrons would have a charge of 96,485 coulombs. Let's do a check on that and see if that would be true. So let's take a mole of electrons, 6.02 times 10 to the 23rd, and multiply by the fact that we claim that each electron has a charge of 1.602 times 10 to the minus 19 coulombs. If we do that, we get a number of 96,440 coulombs. That doesn't seem to match the number we claim should be the total charge on 1 mole of electrons. Well, we can do a little better if we use all available significant figures. Avogadro's number, the version we normally use, does not include all the known significant figures for a mole, and we were certainly not using all the significant figures for the unit of charge. So when we do that, we actually do come out to 96,485 coulombs. Now, if we had an instrument or a device that measures electrical charge, we would actually have the ability to count the number of electrons flowing through the circuit. We will later identify 96,485 coulombs per mole of electrons, coulombs per mole, as something called Faraday's constant, but we'll get back to that. Okay, let's put our diagram back up of electrons flowing in a copper wire from A to B. In addition to electrical charge, in which we're counting electrons, we will find it useful to know the rate of charge flow. Now, this allows us to introduce the concept of current. A current of 1 ampere, or 1 amp, or 1A would be the symbol for amps, means that charge is flowing at the rate of 1 coulomb per second. Let's do an example calculation. How many moles of electrons will have passed from point A to point B if a current of 2.5 amps flowed for 3 hours? So what we want to do is actually count how many moles of electrons will pass from point A to point B if this current, this rate of charge flow, is going on for 3 hours. We can do this calculation by taking 3 hours and converting to seconds, and then multiplying by the current, which is 2.5 coulombs per second, and then multiplying by the fact that we know that 1 mole of electrons has a charge of 96,485 coulombs, and we'd find out that 0.28 moles of electrons have flowed from point A to point B. So knowing the current, the rate of charge flow, and the time of that current flow, we can actually count the number of electrons flowing from point A to point B. Keep in mind, a common unit of current, especially for small electronic devices, is actually the milliamp instead of amps. A milliamp, of course, would be 0.001 amps. Here's our diagram once again. We now have our electrons flowing from A to B in the diagram. Now, in addition to charge in coulombs and current in amps, we need to introduce what's called electromotive force, EMF, which is expressed in units of volts, V. It's quite common to just see the word potential substituted for electromotive force. In electrical circuits, voltage is often described as the pressure of the electron flow caused by a difference of potential, sometimes called a potential difference or just potential, between 2 points in the circuit. And it could be point A and point B. A difference of potential would cause electrons to flow from point A to point B. Now the pressure that's causing the electron flow from A to B could be applied by an outside power source. For instance, if we're pushing electrons uphill energetically, as you would if you were recharging a battery, or the pressure that could be caused by the electron spontaneously falling through a potential difference and supplying power to a device. Now in my diagram here, I don't have these flowing uphill or downhill. Wires don't have to be uphill or downhill for electrons to flow in one direction or another. That would be silly. But the point here is that electrons will flow from A to B if either they're pushed by, for example, hooking this up to a battery and pushing them through, or if they're falling from a state of higher energy to a state of lower energy, in other words, through a potential difference. 1 coulomb of electrons would require or release 1 joule of energy when climbing or falling through a potential difference of 1 volt. That is, 1 volt equals 1 joule per coulomb, or 1 V equals 1 J over capital C. Again, for small electronic devices, a common unit of potential is actually the millivolt rather than the volt. Millivolt being 0.001 volts or 0.001 joules per coulomb. Here's an example question. Suppose you were attempting to recharge a AA battery. How much energy in kilojoules would be required to push 1 mole of electrons uphill through a potential difference of 1.5 volts? Well, how would we deal with this? Well, we need to push 1 mole of electrons. 1 mole of electrons would be 96,485 coulombs. We want to push this through a potential difference of 1.5 volts, which would require 1.5 joules per coulomb, and we'll convert joules to kilojoules. So we find out that we would need 145 kilojoules of energy to push 1 mole of electrons energetically uphill through a potential difference of 1.5 volts. This would be the work we'd have to do to recharge that battery. So let's look at a summary of our electrical terms. Remember, charge, 1 mole of electrons has a charge of 96,485 coulombs. Current, 1 amp, is the rate of charge flow of 1 coulomb per second. Voltage or potential would be 1 joule, 1 volt would be 1 joule per coulomb. Now let's return to redox reactions and try to apply these terms, starting with voltage or potential. It is possible and quite common to express redox reaction spontaneity or non-spontaneity in terms of potential or voltage, and not just in terms of free energy change. Let's go back to our favorite spontaneous redox reaction, the reduction of copper 2 plus by zinc metal to form zinc 2 plus and copper metal. we calculated before using free energies of formation that the overall free energy change for this reaction was minus 212.6 kilojoules. It's very spontaneous. Now we can express the spontaneity of this reaction in terms of potentials or volts in the following manner. The first thing you want to do is split the reaction into oxidation and reduction half reactions. We ought to be able to do this now after practicing balancing redox reactions. Here we recognize that the oxidation half reaction was zinc on the left going to zinc 2 plus on the right, kicking out 2 electrons. So zinc has lost 2 electrons. And the reduction half reaction was that the 2 electrons from the zinc metal are reducing copper 2 plus ions to copper. The next thing we'll do is we'll use what's called tables of standard reduction potentials, which I've labeled E superscript 0, standard, that would be the superscript 0, to assign potentials to each half reaction. We're going to assign voltages to each half reaction. We'll then add up the half reactions to give the net overall potential, or the net standard potential, for the redox reaction. The table here are simply sample standard reduction potentials from a larger table that we'll look at a little bit later. I write the 2 half reactions here, and I make a column for the standard reduction potential, or here it's probably better to say just the standard potential. And I'm going to write here plus 0.763 volts. It's important to realize where I got this number on the table and where I got the sign of this value. If you look on the table for a reaction that involves zinc ion and zinc and 2 electrons, the standard reduction potential listed is minus 0.763 volts. Notice, though, that I wrote next to this oxidation half reaction plus 0.763 volts. Why did I change the sign from what was written in the table? The reason I did that is that, for reasons that will probably become evident to you later, all of the reactions written in this table are written as reductions. Zinc 2 plus 2 electrons going to zinc. I'm interested in the oxidation, which is the opposite of this. When we reverse a reaction that's written in the table here, we change the sign. So I use the number 0.763 volts, but I changed the sign because the table lists reductions, but this is an oxidation. How about the reduction half reaction? That value we can read right off the table, and that's plus 0.337 volts, and I got that from this reaction in the table, copper 2 plus 2 electrons going to copper metal, and I can read it right off the table because it's written as a reduction. Note that there's another reaction involving copper 2 plus on the table, copper 2 plus 1 electron going to copper plus. We don't use that because that's not what's happening in this reduction half reaction. This specifically says copper 2 plus 2 electrons going to copper. So we use the reaction that looks like that from the table. Now what do? Well, you add up the half reactions, and you know what that's going to look like. And then you simply add the standard potentials. We have a plus 0.763 volts and a plus 0.337. So the net overall potential for this overall redox reaction is plus 1.1 volts. Now a net positive value of the standard potential indicates that the reaction is spontaneous as written from left to right. You say, why does a positive value indicate spontaneity? Good question. I'm just telling you at this point that it does. You'll see this a little bit more soon. So both the negative delta G and the net overall positive potential both indicate that reduction of copper 2 plus by zinc is spontaneous, which begs the question, what is the relationship between delta G and the net overall potential besides having opposite sign conventions? Well, let's look at that. The direct relationship between the standard free energy change and the standard potential for a redox reaction is written here. Delta G equals minus NFE, where delta G is, of course, the free energy change in joules per mole. This is often converted to kilojoules per mole. N here is the number of moles of electrons transferred in the balanced reaction as written. This will become more obvious as we do some examples. F is that Faraday's constant I told you about earlier, 96,485 coulombs per mole of electrons. And of course, E0 is the overall net standard potential, which would be in volts, or in other words, in joules per coulomb. Let's do an example. On the previous slides, we independently calculated and compared the values of delta G and net overall potential for our favorite spontaneous reaction. We said delta G was minus 212.6, the standard potential was plus 1.1 volts, both indicated spontaneity. Let's use this equation that we claim tells us the direct relationship between delta G and E0 and see what we get for a delta G if we use an E0 of plus 1.1. Now you say, well, of course, we'll come up with minus 212.6 kilojoules. Well, remember, we got this value using free energy of formation values. So we're going to validate this number by seeing if you get this number when you use this new relationship between delta G and E0 that we just introduced. So let's just do the calculation. We have 2 moles of electrons, N is 2. Why? Because when you look at this equation, this balanced net ionic equation, the number of electrons transferred is 2. Zinc lost 2 electrons. Those 2 electrons go to copper 2 plus to form copper. So N is 2, and it's 2 moles of electrons. Faraday's constant, 96,485 coulombs per mole of electrons. And we said the net overall potential was plus 1.1 joules per coulomb, or in other words, 1.1 volts. So we get a delta G of minus 2.12 times 10 to the 5th joules, which would be minus 212 kilojoules, which is very good agreement with the value we got by using free energy of formation values. Let's look at another example of the relationship between delta G and net potential by finally looking at a different redox reaction. So what we're going to do here is use the appropriate standard reduction potentials from the table on the lower right to calculate the net overall potential for this redox reaction, which is written as a net ionic equation. This is actually the oxidation of tin by zinc 2 plus to form tin 2 plus plus zinc. We'll use the overall value that we obtain for the standard potential to calculate a delta G in kilojoules. And from those two results, we're going to try to predict whether tin can be actually oxidized by zinc 2+. In other words, we're going to see if this reaction as written, left to right, is spontaneous or not. So let's calculate the overall potential using the same two steps we did for the previous example. We'll split the reaction into oxidation and reduction half reactions. We say tin is being oxidized, zinc is being reduced, and then we'll use the table of standard reduction potentials to assign potentials to these half reactions. We'll add up the half reactions and the potentials and see what we get. Here's our two half reactions written with a little bit of room between them. We have our column started for our standard potential, and we look in the table for a value for tin being oxidized to tin 2+. Well, of course, since the table only lists reductions, we find a reduction of tin 2+ to tin, but of course we're looking at the opposite, the oxidation of tin to tin 2+. So we use the value from the table, but we change the sign. So we have plus 0.136 volts. And then we look for the reduction of zinc 2+ to zinc in the table. We've seen that before. It's right here. And since it's written in the table as a reduction and our reaction that we're looking at as a reduction, we can read the value right off the table. It's minus 0.763 volts. So the net overall redox reaction, of course, is written here. If we add up the potentials, we get a net overall potential of negative 0.627 volts, which means, of course, since this is negative, that we're predicting that this reaction, as written from left to right, is not spontaneous. We can reinforce this by using this potential to calculate a free energy change. When we do that and realize that, again, n equals 2 here for this reaction, there's 2 electrons transferred. Faraday's constant is 96,485 coulombs per mole. The net overall potential was negative 0.627 joules per coulomb. So we get an overall delta G of positive 121 kilojoules. So the negative net overall potential and the positive delta G value both indicate that the oxidation of tin metal by zinc is not spontaneous. So if you expose tin metal to a solution of zinc ion, there will be no reaction.